Let's solve another problem where we're asked to calculate the entropy change during a process. Water contained in a closed rigid tank, initially at 100 psi and 800 degrees Fahrenheit, is cooled to a final state where the pressure is 20 psi. Determine the change in specific entropy in BTUs per pound mass R, and show the process on sketches of the TV and TS diagrams. So let's draw a schematic of our system. We've got a rigid tank filled with water, and we'll draw our system boundary around the water molecules. We'll take that as our system. And our given data for this is that state 1 is at 800 degrees Fahrenheit and 100 psi, and state 2 is at 20 psi. So this is a cooling process. And we're going to model it as a closed system, ignoring any changes in kinetic or potential energy as being insignificant. And this is a constant volume process because we're dealing with a closed rigid tank. And we want to find the change in specific entropy in BTUs per pound mass R. So let's find some properties for state 1. We know we'll start in the saturation table at 100 psi. And I noticed that the saturation temperature at this pressure is 327.86 degrees Fahrenheit. Now, the temperature of state 1 is 800 degrees Fahrenheit, so it's much higher than the saturation temperature. So that implies that this state is a superheated vapor. So I'm going to go into the water superheat table at 100 psi and 800 degrees Fahrenheit. I'm going to grab a couple of values here. I'm going to grab the specific volume and the specific entropy for state 1. Now we need to find the same properties at state 2. Well, we have two independent properties that define state 2. The first is its pressure at 20 psi. But we also know its specific volume. We know V2 is equal to V1 because in a closed rigid tank, the volume is constant and the mass is constant. And so the specific volume is constant. So V2 is also equal to 7.445 cubic feet per pound mass. So I'm going to get values of V sub F and V sub G from the table so I can compare our actual specific volume. And we see that V sub F is less than V2 is less than V sub G. That implies that state 2 is a saturated mixture. So while I'm in the table, I'm going to grab values for S sub F and S sub G because we're going to need to calculate the specific entropy at this state. And first of all, of course, I need the quality. Well, I can do that with the specific volumes because the quality is just V2 minus V sub F over V sub G minus V sub F. And I have all of those values. So I calculate that the quality at state 2 is 0.3701. So let's plot a TV diagram of this process. We know that state 1 is at 100 psi and 800 degrees Fahrenheit, and we also know that that's a superheated vapor. We know that the process takes place at constant specific volume to state 2, which we also know is a saturated mixture, and it's at 20 psi. And the saturation temperature at 20 psi is 227.96 degrees Fahrenheit. So that's the temperature at state 2. So now we can calculate the state 2 specific entropy. S is just S sub F plus the quality times S sub G minus S sub F. And we have all of these values. I'm going to calculate that S2 is 0.8525 BTUs per pound mass R. So now we can calculate the change in entropy. Delta S is just S2 minus S1. And we looked, we just calculated S2 for the saturated mixture, and we subtract from that the value of entropy at state 1, which was the superheat value, and we get that delta S is minus 0.9924 BTUs per pound mass R. So we see that the system specific entropy decreased with this negative sign. So let's draw a temperature entropy diagram now. We've got our vapor dome. And we know that state 1 is superheated at 100 psi and 800 degrees Fahrenheit. And we know that state 2 is a saturated mixture at 20 psi. And we know that its quality is about 37%. So I'm going to kind of draw it here on the left side of the vapor dome. And we don't know the path between state 1 and state 2. Normally, I would just draw any dotted line between state 1 and state 2, just to indicate that we got between state 1 and state 2 somehow. We started at one state, we ended up at another state, but we don't know the path that was actually followed during this change. Now, because there's a phase change, we could probably draw that line representing an unknown path a little better. It would have a certain path from its superheat phase until it became a saturated vapor, and then it would probably have a slightly different path from once it starts condensing until it reaches state 2. But still, I've also shown that as a dotted line because we don't know the real path that the process followed.